Hello, this is Dr. Liu, and we have in this video graphical analysis for motion. This was a problem that we previously discussed. A diver bounces off a diving board, and I removed the question parts. I just had the information about her dive. So she starts off at this height, and this is our x0. And she starts off with this velocity, so v0. And if I only have these two pieces of information, I sure can't really solve anything. But let's see what we can do with these information. So let's plug them into equations. Equation 1, we have x0. So x is equal to 1.8 plus 4t minus, again, half 9.8, 4.9 t squared. Now we can't really solve for x because we don't know time. And equation 2, we have velocity equals 4 minus 9.8 t. We can't solve for velocity either because we have three unknowns, right? Position, velocity, and the time. Seems like this is useless, but it's not. If you look at this equation here, if you consider x as a function of time, then the function of time is a quadratic function with a negative coefficient, quadratic coefficient. Then there's a linear term, there's also a constant term. So this can be graphed on a graphing calculator or maybe a graphical piece of software. And this is also a function of time. V as a function of time. This is a linear function. There's a constant term, there's a linear term. So we can graph both, but we should probably graph one first, the position. So this graph will tell you how the position is going to change with time, and it is very useful. We can take a look. So let me grab that graphing calculator program I have. Alright, so over here I have 1.8 and 1.8 plus 4t minus 4.9t squared. So it's all in here. Oops, let's bring it back. It looks like I cannot really just hide the left panel without also minimizing the right panel, and that's okay. So we have this all here, and let's inspect this graph. So we have t here as a horizontal axis, and we also have x as the vertical axis. And she starts at time 0, so right here, and she starts right here. So if you can see it here, right here 1.8, roughly 1.8 here, the crossing. So that's her initial height. She jumps up, so her height goes higher and higher, and then she stops in mid-air. I think we solve for that height. It's 2.62 meters. So that makes sense. There's actually a screen reader, but I can't really point to it. If I point to it, I move my mouse. So if you want to look at it, it's on the bottom left of this window. It's right here. Oh, okay. It wasn't moving. All right. So right here, this is maximum height, and her height starts to go down, down, and down, and down. We know that here, this is where the free fall stops. Her feet hit the water. She undergoes something different than just free fall under gravity, right? And also this part is not really the motion because she starts off here. This region is where the free fall happens, but still is useful to have the whole graph here. And let's use a neat feature here, the tangent line. So I can drag this tangent line. So this right here is the line. So let's move the tangent line right here to the beginning, the time t equal to 0, and you can see here. Okay, right here. I can't really point because I would be moving, but if you can see here this box here. This value before the x is exactly 4.0, right? 4. So it looks like this slope of the tangent line is the velocity, the initial velocity, right here. And this is still true if you progress further. See this? And this value drops from 4 quickly to about 3, 3.5, 3, 2.6, 2.5, right? So as the tangent line starts to get flatter and flatter, the slope gets less, and that's the same as the speed. Speed also gets less. See here, the top. I can't hit the exact top. Maybe I can. Ooh, that's really smooth. It's hard to maintain the top. Right here, about top. So we have almost a zero slope. It represents a zero speed, right? So it looks like a tangent line on the position versus time graph. The slope of that tangent line is exactly the velocity. So now past that point, see this red area here, it represents a negative slope. So that's correct. We have a negative velocity past the maximum point. It comes down, right? So a negative velocity with a negative slope. So velocity is exactly the slope on this position versus time graph. That's what we just learned out. This is really cool, right? So as she jumps up, she has a positive velocity, but a negative acceleration, which causes her velocity to reduce to 0, keeps reducing into a negative range, so she comes down, and then more and more negative as she hits the water, right? Okay, so let's go ahead and hide that, and we'll move to the velocity. Here we have the velocity as a function of time, starting with 4 meters per second with that rate of change, negative 9.8. So we see, let's show this. Okay, we see this slope here. Let's try and scale it a little bit. Okay, so we just see this straight line. So it seems like with a constant acceleration motion, the position is a parabola. It could be right side up or upside down depending on the acceleration. So the velocity is a straight line because if you think about it, you have a constant acceleration. Your velocity changes constantly with time. So the slope must be the change of time, rate of change of velocity, which is acceleration. Let's see that. Okay, so here's just one constant slope, and you can see right here, I don't even have to put my cursor right here because this whole thing has the same exact slope, minus 9.8, right? So the slope of the velocity versus time is acceleration, and the slope of position versus time is velocity, right? So constant slope with a constant acceleration. All right, so let's write them down. So we know that this x looks like this, right? Let's just kind of sketch it. Right, this is time, this is position. So in position versus time graph, we could draw these tangent lines, right? We could draw these tangent lines. So slope of tangent line is exactly equal to velocity. Alright, so past this maximum point, the slope gets negative because she's coming down. Alright, so that is a conclusion. In this position versus time graph. And we can also say that if the acceleration is greater than 0, we have a graph that looks somewhat like this. So it kind of opens up, right? And if the acceleration is less than 0, like the one we have with free fall, negative acceleration, we'll have something that opens downward, right? And what we also learned from this velocity versus time graph, straight line, right? So the slope, this is velocity versus time. So in v versus t, slope of tangent, or actually just a line, is equal to acceleration. That's a bit too much. Equal to acceleration. So this is the graphical meaning of these terms. So the slopes and also the tangent line, how the tangent line moves with its slope. And the slope, if you want to calculate a slope, this is a quick review slope. Is rise over run. So if you have something, say here's a line, so rise is this amount, run is this amount. So here's a right angle triangle. So this is rise. This quantity is run. Alright. Thanks.